Um, Hi everybody, welcome to this AJS. Today with us we have Jessie, Levillain. She's from École polytechnique in Paris. And she will talk about a limiting model for low Reynolds number swimmers with passive elastic arms. So you can start.
Thank you, Irene. So I will be talking about some work I did with my supervisors in Paris. First of all, the setting of this work is we're studying a deformable solid that is surrounded by a fluid. In our case, the deformable solid is really small, like the size of a couple of micrometers, maybe. Some really concrete examples of that is a bull sperm cell, which is swimming with its flagellum. So this one is swimming in a circle because it was genetically modified, but still swimming. And the other one is an algae, Trepsia, which has a very specific movement, which is called metaboly. It's deforming its whole body in order to swim. So those two examples are really small in a fluid and are deforming in order to swim. And the fluid is characterized by the Stokes equation. So the Stokes equation is basically Navier-Stokes, but without the inertial terms, so it becomes linear. And we can neglect the inertial term because of the size of our systems in general. So this is justified by the Reynold number. The Reynold number is the ratio of inertial forces and viscous forces, and in our case, it's really small. So it's really small either when you have a really viscous fluid or when you have a really small system. And in this case, you can neglect the inertial term and the Navier-Stokes equation. In this particular setting, there's a really famous theorem called the scallop theorem, which was announced by Purcell. It states that a reciprocal movement cannot lead to a global displacement at low Reynolds number. So, for example, the scallop, imagine you're a regular scallop, you want to swim, so you open, you move forward, and then you close, and then you open again, you move forward, you close. If you're a scallop of like a couple micrometers, it's not the same thing anymore. You have no inertia, so you open, you move forward, and then you close, you move backwards, and you're stuck like this, and you can never swim. So that's what the scallop theorem is about. And that's why the examples above were trying to find different strategies to move. From the mathematics point of view, there have been different mathematical models of swimmers that can actually bypass the scallop theorem. In general, the key to this is having at least 2 degrees of liberty in your system. So the example we will focus on in this presentation is the one on the right here. It's Najafi and Golestanian's 3-sphere swimmer. It has 3 spheres that are linked by rigid and extensible arms of negligible thickness. So basically, this swimmer has a reciprocal but non-reciprocal but cyclical movement in the sense that in order to swim, it extends one arm, then it extends the other arm, it retracts the first arm, it retracts again the last arm. And so it moves like this in this way, then a little backward, then again forward, and at the end it has like a global displacement. An extension of this was studied by Montino and De Simone. It's the 3-sphere swimmer with a spring. So one of the arms is replaced by an elastic spring. So this time you only have one real active degree of liberty, but actually it can still swim because the string naturally moves out of phase with the arm. So actually it acts in the same way. There's only one kind of drawback. It's that because there's a passive arm, you can only move in one direction. So before you could choose if you wanted to move to the right or to the left, and now you only move in the direction of the spring. So what we did with my supervisors is that we extended this model once more, and we chose to study a swimmer with N springs. This swimmer has the same rigid extensible arm with 2 spheres around it. And then it has kind of a tail of fixed length lambda plus the eventual variation of lengths, composed of N spheres and N springs. So what happens is that if you raise n, if you have more springs, they become smaller and more rigid, and the spheres also become smaller. It's explained here in the parameters. So basically, h is the rest length of each spring, a the radius of each sphere, and k the rigidity of each spring. We also impose that the arm would have a sinusoidal movement in the epsilon cos omega t plus L, and epsilon is the rest length times some percentage of the movement we allow. For this system, we also made some first approximations. So first of all, the first approximation was the stiff force theory, which allows us to compute which force on each sphere using the expression of the speed of each sphere. So you have this vector of forces, which is equal to a matrix times the vector of speed. And in our case, we made an even further approximation at the beginning, which was that there was no interaction between the spheres. And so the speed forces on each sphere only depended on the speed of each sphere. And there's no link between the spheres in the velocities or the forces. So with this, we tried to understand what was going on in the system. The goal was to find an expression for all the LJs below, so the elongation of the string over time. And we were trying to see some kind of sinusoidal movement and maybe some kind of also wave propagating along the tail of the swimmer. So what we did next was two force balances, actually, and plus one force balances, one on the whole system. So again, we have no initial forces. So the sum of the fluid forces is equal to 0. And then a force balance on each sphere. So on each sphere, the fluid forces plus the elastic forces are 0. We also know the elastic forces because we can compute them, saying like on each sphere, you have the elastic forces from the spring on the right and the one from the spring on the left. And from all of this, we can deduce the fluid forces on each sphere, which, using the expressions from the previous slides, enables us to actually find the whole equations of motions for each spring. So this is what they look like in practice with all our first approximations. And it kind of looks like a discrete heat equation. What happens also is that on the right, we put a Dirichlet boundary condition. So there's like a fictitious n+1 spring on the right that has a length 0 and never move. And then on the left, the boundary condition is actually the equation for the first spring, so L1. And it's a Fourier boundary condition. With all of this, we now want to find some oscillating solutions of this problem. So yet another approximation in the first place. We are trying to find complex periodic solutions of this from the one in green. Using the previous equations, we can determine all the coefficients and actually find some expressions that were really ugly. So if you want to see them, you can go on the internet, but I didn't put them here. Then after all this, after having found our solutions, I was saying before that the equations were looking like a discrete heat equation. So of course, what we wanted to do is take our equation, pass to the limits when n tends to infinity in a more formal way and see what happens. And of course, what happens is we find this heat equation with a Fourier boundary condition on the left and a Dirichlet boundary condition on the right. And we call this the elastic swimmer or limit model because then the blue part is composed of an infinity of small spheres and small springs, and it's like an elastic that only retracts and expands in 1D like this. And the question now is, does this model actually make sense? It makes sense on its own, but is it actually really a limit of the previous one? Does the previous one converge to this one? Can we actually prove it without just doing the formal limits? And the answer is yes. Because there are several steps and it's a bit convoluted, but you can actually write the continuous swimmer as a symmetric discretization classic semantic discretization. So you discretize in space and not time. And you have like a classic finite element scheme for your swimmer. Then if you sum for each line of the math matrix, if you sum all the terms and put this value on the diagonal, it's called math lumping, and you get a math lump discretization of your model. And actually, this math lump discretization is very, very similar to the discrete n-string swimmer. So we could view the n-string swimmer as a math lump discretization of the continuous swimmer. And by going through all these steps, we could prove that the math lump phonetic discretization was converging to the continuous swimmer. So we actually have two theorems that are derived from a book by Thomas, who proved for Dirichlet conditions on both ends that a math lump semi-discretization of a problem always converges to the actual problem. And in our case, we don't have the exact same result as Thomas because we don't have the same boundary condition, but we're still able to prove the convergence. So in L2 norm, you have a convergence at first order, whereas Thomas had one at second order, and in the H1 norm, we have it at order 1/2, and he had it at order 1. So yeah, basically you have this big equation, but what we really want to see in practice is if we can numerically see it like on a graph. So, and there are two possibilities for the test, or we directly solve all the equations numerically and see if they converge, or we take our approximations of the periodic solutions, the explicit solutions, and we see in this case if the theorem works. So just for an indication, this is the kind of parameter values we use for our model. So it's, again, it's really small. It matches the 3-sphere swimmer with an arm from Montino and De Simone, because it turns out that we did some tests and we had the same optimal parameters. Yes, the fluid viscosity and all the other ones actually characterize the system. So here are the numerical results for the convergence. We can see that if we compare the continuous model to Thomas mass lumping with Dirichlet conditions or classic discretization, we actually have the order 2 convergence in L2 norm, and with ours we have the first order convergence. And actually for the H1 norm, we also have the same thing. We see this kind of super convergence phenomenon because we only use the really regular periodic solutions. So it's actually better than what we could prove in this particular case. So our only goal was to prove that it actually converges, and we don't really care about the order, so we were happy with this. Then we want to actually compute the displacement of the swimmer, because the whole goal of this was to have a swimmer, so it swims, so it has to move, so we computed the displacement. We start again from the resistive force theory, so the force and the forces and the speed of the sphere have a linear relation using this resistance matrix. And this time in the matrix, we take into account all the fluid interactions between the spheres. So we don't only have the diagonal like before, we had also several terms depending on the variation of length of all the springs. For the LJs, we still use the approximations we computed before, but we just take all of them into account, because otherwise we would fall into the case of the South theorem, where everything is independent, moving on its own, and we actually never swim. So using this, we chose to compute the displacement of the first sphere, so the head of the swimmer, and see if we actually found something. So we computed V1, integrated it over one period, and we find this expression for delta x1. Then, of course, we wanted to see the continuous analogy for this. So passing to the limit in the expression for delta x1, we find the displacement of the head of the continuous swimmer, which is really pretty, but not really usable in practice. So we computed our simulations using a large number of springs and the discrete displacements. So here's the displacement. Here you can first see the displacement of the discrete swimmer for a large number of springs, 2000. Again, stand for various values of epsilon tilde. So epsilon tilde is actually the percentage of, as I was saying, of movement we allow for the active arm. So we see that the more the active arm can move, the bigger the displacement. The other thing that we can also observe is that the swimmer actually goes back and forth over one period before actually achieving a net displacement. So it's like Najafi and Golestanian swimmer, which was doing this, moving backwards, and then finally moving forward. We had the same phenomenon. In practice, the displacement is also really small, which is characteristic of this kind of systems. And we can also see in this graph, so in figure 2, we can see the displacement of the swimmer directly depending on epsilon tilde. And we can see that, as expected for this type of systems, it's in epsilon tilde squared. And there was also an adimensional parameter we introduced at some point when computing the solutions, which depends on the rigidity of the springs, the size of the spheres, and the oscillating frequency of the arm. And we can see that there's an optimal value in figure 3 for this parameter. So it's around 0.37, at which we achieve a maximal displacement. So actually we can explain this pretty well. So if K omega is really big tends to infinity, it means that either the rigidity of the springs is really big or the frequency tends to 0. If the frequency tends to 0, then the arm is not moving and we're not inducing any movement in the springs later. And then the springs are really rigid. It's just like a rigid part and one arm that is moving, and it's the scallop theorem again, so we're not moving. It's the same thing on the other side if K omega tends to 0. So we had this optimal value, which is again kind of similar to Montino and De Simone's results. Then finally, we can actually see the swimmer in motion. So here in this graph, you can see, depending on the position you are at, so then spring number, the deformation. So it's not, the swimmer is still moving in 1D. That is the amount of stretching of one spring, depending on the spring. So what we can see is that around up until like the 500th spring, so 1/4 of the swimmer is actually moving a lot. We see this real sinusoidal oscillation, and the wave is propagating like for half a wavelength, and then it becomes completely flat. It attenuates really fast. So we have this first oscillation, like the first part is really efficient, and then the other is just like a dead end of the swimmer. It's as if you had like this sperm cell that was really ill and trying to move, and then it would just try to create an impulsion at the start and go and die somewhere. So actually, this made us think of Machin's swimming rod, which was introduced way earlier. So Machin tried to write the equations for an elastic rod that was swimming. He found 4 oscillating modes for his system, but he also saw that his system wasn't swimming very efficiently. So again, he had a propagating wave that was being attenuated after less than a wavelength. And what he concluded from this is that we needed some form of activation along the rod, or in our case, along our springs, to actually get the oscillation along all the tail. And then finally, to conclude, we studied 2 models of microswimmers with only 1 absolute degree of freedom. We can prove the convergence of the discrete model towards the continuous one. However, if we really want this model to mimic a 1-dimensional flagellum, like Machin's, we need to add in some form of activation. So in the future, what we want to do is, first of all, extend this type of convergence results to other models of swimmers. So there's a famous 2D swimmer, which is called the N-link one, which actually angles like this, and it can move in 2D. And we would like to extend our results to the convergence of an ending to a swimming filament. Then we would like to couple our ending swimmer with flagellar activation mechanisms. So this is what we're currently working on with Levillain. And also, if we manage to couple flagellar model with activation mechanism, finally we could perhaps have a comprehensive stem cell simulation. Thank you.
Do you have any questions?
Yes.
Yes.
You said that you use the resistive force theory with all here,
Yeah.
accounting for all interactions. And okay, but I was wondering in that dimensional parameter that you showed. I don't think I know if there is a trace of the viscosity or
In the one from the numerical
Yeah.
test. Yeah, there is.
scale omega. Ah, yeah. So that's yeah.
Okay, so that was your question.
I mean, yeah, essentially, yes. I didn't remember the.
Okay.
Maybe, I mean, the extension. Can you quantify or see how much the hydrodynamic interaction accounts in the simulation compared to the springs?
We didn't run tests on the value of the viscosity alone, so we only did tests on K omega or K or omega or 8.
But the L0 thing is the length of the length of the first order.
Yeah, over time.
So it just moves in this one direction.
Yeah.
Okay. But still the whole systems space.
Yeah, it swims, but only in one direction as well.
Something like that. This one maybe. Oh no, it's not.
This one, yeah.
Yeah.
Yeah, so this one is, it's a graph of something that is happening in 1D, but the graph is in 2D.
Okay, so. So the meaning is that the last part of the sequence of springs stays the same, doesn't get compressed.
Yeah, it's always like equilibrium.
Is that any meaning of the length of where it's actually compressed? Just an observation.
It's an observation, but it's the same one as matrix. So I don't know if there's an actual formula to compute this, but it's always less than the wavelength.
But this one is in
This one is in 2D.
Okay. There any practical mechanical examples of things which are just one dimensional?
Not really, no.
Would you have other questions?
I don't know if you are thinking about it, but
Maybe I'll ask later.
maybe that's good, okay. Okay, so I don't know if you have any other questions.
I was wondering about the two-dimensional case you mentioned for the microswimmer.
Yeah,
You wanted to do something using springs as well, or just letting them to infinity and the length of the links to zero?
so it's in the case of the 2D one, it's just segments that
Yeah.
can move with an angle. So there's no
you're
spring.
not using springs.
No.
So, thank you, Jessie, again.